On this second segment of the lessons, we will deal with types and objects in Julia. Please run this code on a new Julia process and run as before these commands in order to set the working directory and the environment to the directory of the first lesson. One note about types. This is important because from this one derive much of the power of Julia. So Julia is just in time compiled. What is it? When we define a new variables, the type is inferred from the information. So here a equal to 1 and b equal 1.0, the compiler inferred the type of a and b from the information that we give it, and the type of a is an integer and type of b is a float. The default one for integer and float are integer int 64 and float 64. Now, what if we, so attention, but they are not the same. They can be converted, and we're going to see in a second, but they are not the same. And so you need to put attention on this one. So if you have an integer and you want, very often this is done automatically between integer and floating, but sometimes, depending of the case, it's not automatically. So you need to convert from one type to another, and you use this syntax here: convert, and then the type where you want to convert, and the object that you are converting. So now b is a float. Started to be an integer, but then you convert the integer in a float, and you obtain the type that you want. Julia organizes the type in a nice hierarchy. At the top level, there is the type any, but is it something that the compiler doesn't have any information about it, and it can become at runtime whatever is needed. And this any then is divided in several, it has several childs. One is abstract string, another is abstract array, and then this abstract string, abstract array have some concrete type called strings, array, and so on. We will go more in details about this difference between abstract types and concrete type. One will deal with user-defined types. But for now, just observe that the types is organized hierarchically. And in particular, the number type is pretty well, pretty extended. So we have rationals, we have complex, we have real rationals, integer, signed integer, we have abstract irrational, abstract float, and so on. And you can have the full complete number hierarchy at this address. Another characteristics regarding types is that in Julia, really everything is an object that is it of some sort of type. So if we say C is the type of A is an integer, C is not an object integer. C is the type integer, is the type itself, and even the type itself is an object, and is an object of type data type. Okay. Further, if we have a functions here, syn functions, okay, is the common defined a primitive in Julia, is already defined in Julia, and we can see that here type of D is a child here. This symbol here is to say, we'll see again in the types, but here is to say that this type here is a child of the type functions, and even the operators like the addition, the plus is a function, and this is very, very powerful because when we do 1 plus 2, what really Julia does is that nothing else than rewriting here in this form. So to call this function that happens to have the name plus, but could be called foo or could be called whatever name. So this is nothing else than a functions with 2 parameters, 1 and 2. So when I call this one, when I actually use this syntax, Julia rewrite in this form and call these functions to obtain the results. Julia is really, really powerful because even the defined operator can be changed. I need first to import them from base, and then I can do whatever crazy I want. For example, here I uncomment here, and I say that I want define a new addition with 3 parameters, and I do the multiplication of these 3 parameters, okay? And now when I do 10 plus 20 plus 30, what will happen? I redefined the meaning of the addition, and I obtain the multiplication of the 3. Notice that the way I define it here is with 3 parameters. So this is different than with 2 parameters or with 4 parameters. So if I use 2 parameters and or 4 parameters, I'm still calling the original plus operator. It's only with 3 parameters that I change the meaning. However, even with 3 parameters, it's pretty dangerous what I done, and at this point I'm going to restart Julia because if you and you should do the same, because if you keep plus defined in this way, even if it's with 3 parameters, there will be a lot of problems that you will have further, because of course with great power come great responsibility. So please, I show you this one, but in your code don't do things like this one. So I have now restarted the Julia process and run this code again. It may take a few seconds on your computer in order to get rid of this strange definition of the addition function. But what does exactly happens when we'll run a command like this one, k equal to 10? Well, actually, it happens 2 different things. First, here we create an object of type integer 64 in memory, okay? And then what we do, we bind this object to the k identifier, so the variable names. In R, for example, the syntax would be something like k arrow 10 to indicate that we really allocate this object here, and we associate this object here to the name k. So as we said earlier, as we did earlier, we say that we have an integer object, okay? We can see here the size of k, and the size is 8. Why it is 8? We can also print here with this bit string functions, and we can see that it is 8 because here we really created an object that in every of this digit is a bit, and 8-bit is a byte, and we have integer 64. It is a set of 8 bytes, and indeed here in this case 10 is nothing else than this is the binary representations, and we can see that is so this is okay, the binary representation that you see here. So again, here we create this object, we allocate some memory to host this object here, in this case an integer object, and we bind this object to an identifier. What will happen if we run this code here, m equal to k? Well, in Julia, this doesn't create another object, but it simply reassign the same object to a new identifier. So now you have to think that we are not using 2 times the memory, but the same memory where this number, this set of 00001010 is associated to both the identifier k and m. So when we ask if the 2 objects are equal, we get a true, and we do that with the double equal sign. In Julia, you have another comparison operator with 3 equal signs, but tell us if the object is actually the same. In this case, should be true, because both m and k do reference the same object in memory. Okay, so when this is important, when in Julia, when you say that one identifier is equal to another one, it means that you reference the same object. You bind the same object that is referenced by k also by the identifier m. This is all what we need to know about memory allocation in Julia, at least for now. In particular, what I want to say is that Julia has a so-called garbage collector that automatically cancel all the objects that are no longer accessible by any part of the code. For example, when you type this k equal to 10 inside a function, k is a local variable. So you, inside a function, you create this object, you bind it to k, but when the function returns, this object is still there, but is no longer accessible by any other parts of the code. In this case, in case like this, it will be removed from the memory at the next instance of the garbage collector. So Julia has this garbage collector that automatically runs very frequently across the run of your program, and automatically cancel all this kind of objects that are no longer needed.